So what we are going to continue with our how we just try to introduce non-Euclidean geometry. So we are going to just have some discussion about fifth postulate. So the existence of fifth postulate, even though it's part and it may be part and parcel of Euclidean geometry, stating it separately has some reasons historically, because there have been always in the history of non-Euclidean geometry there have been what I should say a sort of discomfort regarding the logical completeness or of this postulate, and the fifth postulate. Maybe to quote, if I quote this book, so maybe the perhaps the most famous single utterance in the history of science, according to this Kaiser. So it's one of the. So if it's because this fifth postulate has very much interest upon how we understand geometry and in a larger context. So before we are going to start with the how description of fifth postulate, which we know intuitively in your earlier high school textbooks, the point to emphasize is that the fifth postulate is stated in different ways in different books. So one is Playfair's axiom, or the point that through a given point only one straight line can be drawn, which is parallel to a given line. So this statement is stated in many ways, or there can be many exercises we can arrive at this statement. And the point is that we have to arrive at this statement modulo that if we don't take the validity of this statement, it will lead to contradictions. So we'll take 1-2 steps which will try to just emphasize this point, that if we don't take the thing in that sense, it should lead to contradictions. For example, there can be a proposition that if a straight line falling on two straight lines, if a straight line falling on two straight lines makes alternate angles equal to one another. So it means that the straight lines are parallel, as we know. Lines are parallel. We know it. We have been knowing it. But if you assume that the angles, for example, if there are two parallel lines and there is a point A, B, C, and D. So if alternate angles are equal or corresponding angles are equal, so we know that these parallel lines never meet. Assuming that they will meet, assuming that will take proof by contradiction. So assuming that if they will meet at some point, we can take it like this. So we assume that they might be meeting at the point P. So if you assume that they might make P, so how it will lead to contradiction? So it means that, for example, we always know that. So if you assume that AB, this parallel line, and CD, they don't. If there are parallel lines, they extend to infinity. So if you assume that they don't meet in infinity, they will meet at some point. So if we extend them, extrapolate them, so maybe they might so assume. So what is the contradiction it will lead? So for example, so in a triangle, the exterior angle CTS, exterior angle CTS. So this angle CTS is equal to the interior of the opposite angles. So CTS is equivalent to the interior of opposite angles. It's equivalent to maybe TSP. So it's equivalent to this. So it's not. So you don't assume it's. For example, normally when the two lines are parallel, these alternate angles are equal. So since we are not assuming that they will be exactly parallel, so the line is not SB. So because they are going to meet at some point in P, so we can say that in some sense, so we can take it. So this is not that line. So you can take it. It might be like this. So this exterior angle CTS should be equivalent to this angle, what I should say, because if they are going to meet at some point, so exterior angle is equal to TSP. Exterior angle in the triangle, exterior angle CTS is equivalent to interior and opposite angle TSP. So exterior angle CTS is equivalent to interior angle TSP. So if it is that way, so but it is impossible. Why it's impossible? It follows that AB and CD cannot meet in the direction opposite to B and D. So this means that AB and CD cannot meet in the direction opposite to C and D. So if you assume that they are going to meet this way, so it means that, so it will lead to some contradiction. In the opposite direction, they are not going to meet in B and D, in B and D, in B and D, in B and D. So by similar arguments, it can be shown that they cannot meet in the direction of A and C. In the same way, if you just do the construction backwards, you can say that they cannot also meet in the backward direction A and C. So it will lead to some sort of contradiction. So in the same way, for example, if a straight line, so there can be another proposition. So if a straight line falling on two straight lines makes an exterior angle equal to the interior and opposite angle on the same side. So we know that so if we know it from our, so if a straight line falling on two straight lines, so if a straight line is intersecting two, if the straight line is intersecting two lines, and we know that the interior angles of them, they are two right angles, or if a straight line is perpendicular on two straight lines, which means the sum of interior angle is 180 degree. So we, from this thing, we know that the lines should be parallel. The lines should be parallel. This we know. So how it will help? So what? So in the if you see the Euclid's elements, Euclid has used this thing as prolix, or you see. So if Euclid uses the name or the term for this fifth postulate, it's also called prolix or fifth postulate, or it's frequently also referred as parallel postulate. So if you go to Euclid's elements, the way it is stated is it's stated that that a given line which is perpendicular to two given lines, or the sum of the interior angles is a 180-degree, so the two lines will be parallel to each other. So this is the statement in the this thing. Now the point is that a straight line falling on parallel straight lines makes an angle alternate angle straight. Now the another proposition is there. The other proposition is that a straight line falling on a straight line falling on parallel straight lines falling on parallel straight lines a straight line falling on two parallel lines makes an alternate angles equal to one another. So if you know, I'll just write it in terms of that. Makes alternate angles to each other, such that the exterior angle is equal to the interior opposite angles. So the exterior angle is equal to interior. So such that the exterior angle is equal to the interior this is exterior angle is equal to the interior angles and opposite angle, and the interior angle is on the same side are equal to two right angles. So the sum of these two angles, or sum of this angle and this angle, it is 180-degree. So what I'm going to say, maybe I'll just wait a bit because of this azan. So if you assume from this proposition that at a straight line falling on two parallel straight lines makes an alternate angles, so exterior angle is equivalent to the interior opposite angles. So if you assume, for example, if you take two lines A, B, A, B, C, D, T, S. So if you assume that BST is is greater than CTS. So if you assume that BST, this angle, BST, if you assume that BST is greater than CTS, so normally we know that alternate angles should be equal. So if you assume that this is greater than this thing, so this follows that the sum of angles BST, and DTS, BST and STD, or BST or T or STD. So if you assume that this is greater than this angle, so this means sum of these two angles can be greater than two right angles. Or if you assume that this is less than this angle, so it will also correspond to the fact that the sum of two angles is less than two right angles. In both cases, then if it's less than, so this AB and they should meet at some point. So if you assume that the one of the alternate angles is not equal to other alternate angle, it is greater than this, then what it will lead to? It will lead that these two lines will somehow meet at some points, maybe not in a forward direction, in backward direction, if it is greater than 180 degree. So if it's less than 180 degree, it's going to meet at this point. So from this, we conclude that BS. So we conclude that it's again proved by contradiction. So we conclude that BST should not be greater than this CTS, and vice versa. So there's a discussion in the book that whether the statement that the Euclidean axioms or statements are self-evident truths of geometry, whether they should hold or not within this context, because so there have been numerous attempts have been made to prove this postulate by altering the definition of parallels. So if you alter how we define this parallel statement, there are ways of stating this parallel statement. So it will lead to some things. It would lead to our question whether the assumption that this is an self-evident statement or truth, that whether it holds or not. So to make the point more, not to come to the maybe the textbook way of stating normally how textbooks state this parallel postulate without worrying or making an due to those parallel definitions. We state a popular way of stating this Euclid's fifth postulate as something called Playfair's axiom. Playfair's axiom. So through a given through a given point can be drawn only one parallel. Through a given point can be drawn only one parallel line. So it's as simple as that. So if you want to state without going into the details of it, so this is the more popular way of how we have studied since our earlier classes, how it's stated in books. Through a given point can be drawn only one. Through a given point can be drawn only one parallel line. The straight line is mean it's implicit. So on for a given straight line, or the other way from two given straight two parallel lines. If a line is if you draw a parallel line from a given point to a given line, and that there is another line which is parallel to the given line, the two lines can also be parallel. So this is a conclusion of it. So where is the problem? The problem is, like for example, not problem in that in the conceptual sense, problem in the self-evident sense. For example, if we just draw a parallel line, if you draw a parallel line like this, and this is this, and so this is this, this is this, this is QR CT. So if you have this is one straight line, so you can see it. This is a straight line, so which is cutting in a transversely. It's being cut. This straight line. You have another straight line. So we have another straight line. So you can have A, B. This is CD. So this is QR. So if you construct it that way, so we say that construct through S the line SQR. So if it's a straight line, this is another straight line, but you construct through this line, but this straight line cuts not only this line but also this transverse line. But you draw another straight line which cuts transversely this straight line also, so that this line is parallel to this line. So if that is the case, then so construct through S the line QSR, making the sum of angles RST and making the angles RST. So this angle RST or angle RST. So RST and DTS, they are two right angles, as you know. You can see it. The sum of two interior angles in a given parallel lines, they are two right angles. You know it. Now, since QSR and ASB are different lines, and by Playfair's axiom, only one line can be drawn through S parallel to. So even though this is another straight line, so but what if you just stick to Playfair's axiom, only one line can be drawn which is parallel to this very line. Only one line can be drawn which is parallel to this line. which is parallel to CD. And we conclude that AB meets. So if it's not that way, this means that AB should meet CD. AB should meet CD. So these lines meet in the direction of B and D. For if they meet in opposite direction, a triangle will be formed such that so if they meet in opposite directions, so these lines meet in B and D. So if they meet in opposite directions, the triangle will be formed with the sum of two angles greater than two right angles. So if they form in the opposite direction, so we could have triangles whose sum is greater than two right angles, which is a sort of contradiction by our previous statements, the way we have constructed. If you just go through this book, section 1 and 17, by that logic, this will lead to contradictions. So the point to emphasize is that constructing a given line this way and if these two lines somehow meet, and if the triangles which are formed by the backward extrapolation, they will lead to the formation of triangles which may be greater than two right angles, and this is a contradictions. And so we are going to stick to Playfair's statement of, or rather, if I just use the phrase the book has used, is that all additional assertions or additional assertions are needless for superfluous for the faith of the learner. So to put it straight is that we have to make statements the way in Okuman's thing. Statements have to be made simpler, or entities have not to be multiplied beyond necessities. So that's in Okuman's way of stating the things, but so if we do things this way, now what we are going to do is we are going to have so from this previous action, you can also have there can be one or two exercises which you can attempt. So for example, one of the exercises I'll only state that if a straight line intersects one of the two parallel lines, it will intersect the other. It will intersect the one. If a straight line intersects one of the two parallel lines, so if a straight line intersects one of the parallel lines, so it will also intersect other. So it's an exercise you should attempt at. Or the other statement is straight lines which are parallel to the same straight lines. So if two straight lines are parallel to the same straight line, they are parallel to each other. So this is, and also a small exercise in which you can always attempt to just make things evident in the Euclidean sense. Now what we are going to do, we are going to have one or two other ways of also arriving at the fifth postulate. The other ways of stating the same things. One is through one way. So we are going to the way. This is the simplest way of stating the Playfair's action. But there can be more alternate ways of stating the fifth postulate or Playfair's action. So what more? So before we are going to use the triangles, with the sum of the three angles of triangle, they are equivalent to 180 degree. So this statement we are going to use, and maybe a couple of other things. So this, for example, or the sum of angles of the triangle are equivalent to two right angles. So or and this is one thing. The other is that we are going to use an exterior angle of triangle is sum of two opposite and interior angle. So you know, your exterior angle of triangle is equivalent to sum of two interior theta 2 theta 1. So if it's a right angle triangle, so you can say that exterior angle of a triangle is equivalent to sum of two interior angles. So these two statements, which you know from this statement in your earlier classes, we are going to use these two statements to prove a point. That through a given point only one line can be drawn, which is parallel to which can through a given point only one line can be drawn, which can be which is parallel. So if you have, for example, to come to this point in another way, for example, if you have, we are going to prove a lemma 2, that through a given point P, there can always be a line with a given line P less than any given angle alpha, however small. So through a given point P, there can always be a line with a given straight line P less than any given alpha. So if you assume this diagram will make it things clearer. So if you have a line like this, so if you have a line, so this is a parallel line. So apart from this line, which is supposed to be exactly parallel, we can have infinite constructions of lines which have overlapping angles, which can be made consecutively smaller and smaller in that sense. So for example, so if you have this is theta, this is 1. So if you have A1, this is A2, this is another line, A3, so on, A4, A5, AN, and AN minus 1, and last one is AN. You can see it, AN minus 1 and AN. So this is theta, this can be theta. So you can have one line, the other line, but the angle which you can make, but the last line which can make, which is parallel to this line. So it's going to be these are smaller. So the last line can be this one, which is exactly parallel to this line. So to come to this point, so we'll say, for example, so if PA1, so if you say this is P, this is B, and this is also P. So this is A1, A2, A3, and so on and so forth. So from P, draw PA1 perpendicular. So we can draw PA1 perpendicular to it. So measure A1, A2, measure A1, A2 equivalent to PA1. We'll just keep this equivalent to, so we'll keep this equivalent to this. in either direction of P. So designate that theta equal angles A1P. So we make these two angles equal. This is angle is equal to this angle. This may be a perpendicular. You can see it. So if it is that way, so you can see. So if it is this 180 degree, so you can see it. You can say it theta plus 90. Theta plus 90 is going to 180 degree, if you sum of the angles. So if you take it, so theta, the value of theta will come out to be 90/45, or you can take it as pi by 4. So if it is that way, so now if you measure this angle, so if it's pi by 4, so this 180 minus pi by 4 is 135. It's 45 degree. It's 45 degrees, 135 degree. So you can have it 135 plus theta plus again you can have two angles, theta and theta, because theta is equal to 180 degree, and you can have theta is equal to pi by 4, because it's 2, it's again 2 here. So it is it's pi by 2 square, this one, so it can be pi by 2 cube, so on. So you can accordingly construct angles, this one angle, then this third one, if you just construct it this way. So what the point we are going to prove is that the point we are going to prove is that, so angle PA3 PA2 is equal to angle A3 A3 and P is equal to theta by 2, or it's equal to this one, pi by 2 cube, and so on. So if you go to the angle N, if you go to angle N, then it will come out to be or N minus 1. So angle AN minus 1 PAN, it's equal to pi by 2n. So you can increase the powers of this, so that will lead to this thing. So if you use the postulate of Archimedes, so there exists a number k such that, so by the postulate of number Archimedes, so we can have a number k such that k alpha we can construct a number k such that k alpha is always greater than pi, or pi can be greater than or pi can be pi by alpha. So alpha can be greater than pi by k, or so if you assume that this is in the denominator and this is in the numerator, and you make this correspondence with this, so from this you can see 2 to the power n can be made greater than k. So in principle you can construct you can have such that pi by 2 to the power n is always less than alpha. So we can construct this thing. So we can always have a construction of alpha. So this can always come out to be less than this thing. It's less than this thing. Even if you can include, you can have this thing. So from this, what we have to, the point is what we are going to arrive at. And what we are going to arrive at is so what we are going to arrive at is, so if we draw PA1 perpendicular to P, PA1 perpendicular to P, if we draw if PA1 is perpendicular to P, draws PB perpendicular to PA1. And PB is perpendicular to P. So from this you can have PA. So if you just to make it short, so you can have a construction where angle PA2 A1 plus angle A1P A3. Oh, sorry. PA1 PA2 A1 and this angle plus A1 A3 A1 P A3 A1P A3 this angle. Should be equivalent to oh, sorry, it's PA3 PA3 A1. So this angle plus A1 P A3. So this angle plus this angle. So this angle plus so you can see. So this angle plus this angle plus this angle is 180 degrees, since this is 90 degrees. So this angle plus this angle is 90 degrees. So if it is 90 degree, this is 90 degree. So it's equivalent to angle BPA3 So this angle plus angle A1 PA3. So A1 PA3. So this is also 90 degree. So from this, so whole of this thing is equivalent to pi by 2 or 90 degree. So from this, so this and this will cancel. So what does it mean? So we have arrived at something very interesting. The interesting thing is that BPA3 is equivalent to angle PA3A1. So what does it mean that we have got this angle is equivalent to this thing? BPA3 is equivalent to PA3A1. PA3A1. So this angle is equivalent to. So what does it mean? So we have arrived at this angle is equivalent to. So what does it mean? So PB is the only line P through which P does not cut P. For no matter how small the angle, the angular line through P makes with PB or by lemma to all other lines through P, making smaller and smaller angles PB and cutting P. So that the first line must also cut P. So that the first line. So then PB is the only line through P. So PB is the only line through B through P. PB is the only line through P. So this is the point. So PB, we have arrived at that PB can be the only line through B, or there is only one and only one straight line which will pass through a given point, which should be parallel to a given line. So we have arrived at this construction by constructing corresponding angles to this very thing, such that such that we at the end arrived at this angle. So we can construct only one line which is going to bisect it, which is only, sorry, not bisect it. It is the only line P through which does not cut P PB is the only line which does not. So other lines are cutting. So this line is cutting this thing. This line is cutting this thing. So when you go to infinity like this, so you are going to P and this last line which is not going to cut this line is this line PB. So other lines are going to cut it. So this is the thing we are going to we have arrived at it. So this is another convoluted way of stating. So it might take some time to absorb that from this construction we have arrived at that this thing. This line on one line will be parallel to this given line. And maybe there is some other way of this is one construction. Another construction is from similar triangles or from congruent triangles. If you know, two triangles can be similar, but they need not necessarily be congruent. So using this fact is we are arriving at the parallel postulate. How do we arrive at this postulate? So we can construct two triangles. We construct two triangles A, B, C, D, E. So we construct two triangles. So another triangle is A prime, B prime, C prime. So we have two triangles A, B, C. So it is not congruent, but it is similar to this triangle is similar to this triangle. This means this angle is equal to this angle. This angle is equal to this angle. So before and this angle is going to this angle. Now what we are going to do? We are going to draw another. We are going to make another triangle out of this triangle and make a congruent triangle from this triangle, but that smaller triangle is congruent to this triangle. So if you make it, so this is D and E, such that AE is equal to AC, AD is equal to A prime, B prime. So if you make this construction and it's a quadrilateral which you know, that's it. So now what the book says that viewer can easily show that AE is less than AC. So AE is, so we can show that AE is less than AC. So it's followed from the assumption that AE is greater than or equal to AC, or AE is less than AC for the assumption that AE is greater than or equivalent to AC. AE is greater than or equivalent to AC. AE is greater than or equivalent to AC. A is or equivalent or greater than equal to leads to contradiction. So now, without use of fifth postulation or its equivalent, that is, so the equivalent of the fifth postulate is, or its equivalent, that the sum of angles of triangle can so the sum of two angles which we have used again and again, the sum of two angles of the triangle, sum of the two angles, interior angles which are cut by the parallel lines, they cannot be less than two right angles. Or sum of the angles, so if you just, that's a statement there, but here is that the sum of angles of the triangle cannot be less or greater than two right angles. So that knowledge, that sum of three angles of the triangle is cannot be greater than two right angles. One, And the second is that if one triangle has a sum of its angles equal to 2, then the sum of the angles of every triangle is sum of the. So, so by these two statements, by if one of the triangles has the sum, so if one of the triangles has sum, so the other triangles will also follow the same. So by using these two facts, how should we arrive at fifth postulate? So by drawing B, now what we are going to have another construction. We are going to draw B. So from this construction, if two triangles, there can, so you can extend this statement that triangles, the sum of angles of the triangles cannot be greater than two right angles. So it can be true for non-triangles or similarly constructed triangles. Which follow from that construction. So by now what we are going to do is we are going to draw a line BE. Drawing BE, two triangles BDE, two triangles BDE, and BCE are formed. So this quadrilateral, it can be composed of this triangle and this triangle. So now again the proof by contradiction comes. So if the angle sum of either were less than two right angles, that for the other would be greater. So if you assume that the sum of this triangle is less than two right angles, but it should be accommodated by this thing, because if it's a quadrilateral, the sum of a quadrilateral is 360 degree, or if one angle of the three angles of the quadrilateral 90. So if the quadrilateral can be formed of two triangles, so if the sum of one triangle, the sum of angles is less than 180 degree, the other triangle will have a sum which is greater than it. So that the total sum should be whatever that is. So if the angle for either is less than 2 right, and then for the other it will be greater. So we conclude that the sum of angles for each triangle is equal to two right angles, and that the same is true for every triangle. So this is this thing. Now use the fifth ordinal, the sum of angles of the triangle. So the point is not to prove fifth postulate. The point is to prove that without using fifth postulate, we can arrive at the statement that sum of two angles of the triangle can, sum of the three angles of the triangle can never be less than two right angles. So in the same way, fifth postulate also maybe stands on that the interior angles should. So you arrive at the same statement which is used as an ingredient in this fifth postulate. You can also arrive that statement from using the construction of similar triangles. So this is the point. So there is an indirect relation. Or we can construct, so you can see the proof is in the book, you can construct equidistant straight lines. Equidistant, so the exercise is there. So not do it, you can just have a look how we can construct equidistant straight lines. Or there exists a pair of straight lines everywhere equally distant from one another. So we can construct equidistant straight lines to one another. And the other substitutes are so given any 3 points not lying on a straight line, there exists a circle passing through them. So there are 3 points which are not lying on the straight line. So there you can construct a circle out of that construction. or if three angles of the quadrilateral are right angle 90 degree, the fourth is also accordingly same. Or through, and so this point, maybe this is the first two are, you know it, the third one may need some introduction. Through any point given an angle less than 2/3 of right angle. So through any point with an angle less than 2/3 of the right angle. 2/3 of the right angle, maybe 2/3 of 90 means less than 2/3 of the less than 2/3 of the right angle. 2/3 of 90 is how much? Less than 60 degree. So if there's a if you can construct an angle less than 60 degree, there can be always you can always if this angle is always less than 60 degree, you can always construct you can always draw a straight line which meets both sides of the angle. So you can always construct the straight line which meets both sides of the angle. You can always construct a straight line which meets. So this is this thing. So the one important statement which you can see in the book is that sorry, just read it. What he's saying, without so the specimens are what are the different ways of stating the fifth postulate. But if there would not be fifth postulate, we do not have we cannot arrive at Pythagoras theorem. So this is important thing. So if we don't assume fifth postulate, the Pythagoras theorem doesn't. You cannot arrive at that construction. So this is important point. So you can see how much Pythagorean theorem is important in our construction in mathematics and in general also. And if you, for example, and whole which theory of simpler figures would disappear, the treatment of area would have to be recast entirely. This is one important point. And if you abandon the fifth postulate and replace it by something other things, so you may arrive at very arcane or strange things. And so here we'll stop at it. Next, we'll just continue this how Euclidean geometry, non-Euclidean geometry, or fifth postulates. We're going to delve on it more deeply. Thanks.